हेलो फ्रेंड्स, डियर स्टूडेंट्स। आज हम कांस्टेंट मोशन की स्टडी करेंगे। कांस्टेंट मोशन क्या होती है? इफ़ ए पार्टिकल इज फोर्स्ड टू मूव अलोंग ए गिवन सरफेस और कर्व which may be smooth or rough, then the motion of the such particle is called the constant motion. तो यहाँ पर किसी पार्टिकल को मूव कराने के लिए फोर्सली जो मूव कराया जाता है, उस स्थिति में हम उस मोशन को कांस्टेंट मोशन कहते हैं। या हम दो तरह से एक साइक्लोइडल मोशन लेंगे, चक्रीय गति, और सर्वप्रथम मोशन इन ए स्मूथ वर्टिकल सर्किल स्टडी करेंगे। तो एक वर्टिकल सर्किल में पार्टिकल को हम दो प्रकार से गति का अध्ययन कर सकते हैं। फर्स्ट, वर्टिकल सर्किल में उसके लोवेस्ट पॉइंट ए से पार्टिकल को सर्किल के इनसाइड प्रोजेक्ट करके, और दूसरी स्थिति हम आउटसाइड सर्किल के टॉप पॉइंट बी से फ्रीली उसको गति करने के लिए छोड़ सकते हैं। परंतु यहाँ पहले हम इनसाइड मोशन की बात करेंगे। पार्टिकल को लोवेस्ट पॉइंट ए से सर्किल के भीतर प्रोजेक्ट करते हैं। तो हमें स्टडी करना है अब मोशन इन ए स्मूथ वर्टिकल सर्किल। केस है, ए heavy particle is tied to one end of a slight inextensible string whose other end is attached to a fixed point. Suppose OA is a string and a particle is attached at point A, end point A of string, and O is fixed point. It is projected horizontally with a given velocity u from its vertical position of equilibrium. Vertical position of equilibrium in this case will be OA. Suppose a mass of particle is m, then mg will be vertically downward force in equilibrium position in position OA. When this particle is projected from A with velocity u from A, then we have to discuss the subsequent motion. So first let O be the fixed point, and one end of string whose length is A be attached to the point O, and a particle of mass m be attached to the other end A. Suppose OA be the initial vertical position of the string, and now let the particle be projected horizontally from A with velocity u, and at any time t let the particle be at any point P, such that arc AP is S, angle EOP is theta. In this case, there are two forces which are acting on particle P. One is mg vertically downward and reaction R or tension say T in string OP towards normal inside the direction. So here angle AOP is theta, arc AP is S. The external forces acting on the particles are the weight mg of the particle string vertically downwards, and second one is the tension T in the string acting along the inward normal PO. Let V be the velocity of the particle at P. The tangential and normal acceleration equations of motions are as below. Here V be the velocity at P. Angle AOP is theta and arc AP is S. Acting forces are mg vertically downward at P and along PO this is R or T, tension in string. So velocity components, acceleration components along tangent and normal are given as below. First, equation is this one. Effective force along tangent md2s dt square equals to impressed force in that direction are here component of T is T cos 90 along md2s dt2. So the direction of md2s dt2 is along tangent and in this direction impressed forces are component of mg along this direction mg cos of 90 plus theta, which will be minus mg sin theta, and component of T along this direction is T cos 90, which will be 0. So impressed force will be this one in along tangent and along normal mv square upon rho equals to tension in this direction is T cos of 0 in this direction mv square upon rho effective force equals to impressed force in that direction is component of mg along this direction, this will be mg cos of 90 plus 90 minus theta, which will be mg cos of pi minus theta, and so minus mg cos theta, and component of t in this direction, that is in that direction of PO, will be t cos 0, that is this will be t. So along normal PO, the impressed force mv square upon rho equals to t minus mg cos of theta. Now for circle arc AP is S equals to a theta, where a is the radius of circle. So velocity at that point v equals to ds dt equals to e d theta dt, and second derivative with respect to time t d2s dt square equals to a d 2 theta dt square. So put these values in 1, we get a d theta d2 theta dt square equals to minus g sine theta, and multiplying this equation by 2a d theta dt, and then integrating with respect to time, we will get v square equals to a d theta dt square equals to 2ag cos of theta plus integration constant c1. Initially, particle will be at point A, where at A theta is 0, velocity v is u, and time t is 0. So put this in this equation, we get c1 equals to u square minus 2ac, and put the value of c1 in this equation, we will get v square equals to u square minus 2ag plus 2ag cos of theta. This is relation between v and theta. Also, for a circle, we know that radius of curvature rho is radius a. So using equation 4 and this value of rho in equation 2, we get mv square upon a equals to t minus mg cos theta into v square. After putting v square equals to u square minus 2ag plus 2ag cos of theta, we will get this equation 5. And this equation 5 is gives tension in string. So which is t equals to m upon a u square minus 2ag plus 3ag cos of theta. So equation 4 gives velocity and equation 5 gives tension in string. And now we know that equation 4 and 5 are in cos of theta, and theta is increasing from 0 to suppose at B where theta is pi. So we know that when theta increases from 0 to pi, the value of cos theta decreases from 1 to -1. This gives the least value of v and t, which will be occurs at highest point of circle. Thus, at the highest point of the circle, here B where theta is pi. So equation 4 and 5 becomes, using theta is pi, so v square equals to u square minus 4ac and t equals to m upon a u square minus 5ac. Since at theta equals to pi, cos of theta is -1, so this will be minimum velocity and this will be minimum tension, which will be at the highest point of circle. So from 6 and 7, if u square is greater than 5ag, then neither the velocity v nor the tension T is 0. So the particle will describe a complete circle. And if u square is 2ag, then the tension T becomes 0 at the highest point C, whereas the velocity v does not vanish. U square equals to 5ag, then T will be 0, but v is not equal to 0. So particle will describe circle again. So we conclude that the particle describe the complete circle when u square is greater than or equal to 5ag. Therefore, the least value velocity of projection is described the complete circle will be under root of 5ag. यदि हम किसी पार्टिकल को लोवेस्ट पॉइंट ए से अंडर रूट ऑफ 5ag वेलोसिटी से प्रोजेक्ट करते हैं तो वह पूरा सर्किल निर्मित करेगा. बट इफ u square less than 5ag, then v or t or both may be 0 before the particle reaches the highest point. So first let v is 0 where theta is theta 1. Then in equation 4, which is v square equals to u square minus 2ag plus 2ag cos of theta, we get 0 equals to u square minus 2ag plus 2ag cos of theta 1. This gives cos theta 1 equals to 2ag minus u square over 2ag. This is condition or angle theta 1 where V is 0. And suppose h1 be the height above A of the point where the velocity V vanishes. Then see in this blue figure, at height h1 from A, velocity is 0 and angle AOP is theta 1. So cos of theta 1 is 2ag minus u square upon 2ag, and here h1 is this h1 is radius of circle OA, which is A, minus this distance which will be A cos of theta 1. आधार बराबर A cos of theta 1. So h1 will be A minus A cos of theta 1. And using value of cos of theta 1 where V is 0, then we get h1 is u square upon 2ag. This is when V is 0. 9 number equation. Again, in second case, let t is 0. See in red figure, t is 0 when theta 2 angle AOP is theta 2. T is 0 and height from A is h2. So h2 is radius OA, that is A, minus this distance which will be A cos of theta 2. So h2 is A minus A cos of theta 2. And thus when t is 0, we get cos of theta 2 is two ag minus u square upon 3ag using equation 5. And in this case, the height h2 is A minus A cos of theta 2. Using value of cos of theta 2 from 10, this will be u square plus ag upon 3g. So now there is 3 cases arises. Case 1, the velocity v vanishes before the tension. Suppose the velocity v vanishes before the tension. It means h1 less than h2. h1 where when velocity vanishes, and h2 vertical height from A where tension vanishes. So h1 less than h2, and using value of h1 from equation 9 and h2 from equation 11, we get u square upon 2ag less than u square plus ag upon 3g, or we can say that u square less than 2ag. This is the condition where v vanishes first but tension is still there exists. And using this value of u from 8 as u square less than 2ag, it means cos theta 1 is positive, and from equation 8, and since theta 1 is positive, cos theta 1 is positive, it means theta 1 is an acute angle. Acute angle means angle which is less than 90 degree. So you see in this blue figure, this is theta 1 which will be less than pi by 2. So in this case, if the particle is projected with the horizontal velocity which is less than under root of 2 GA, then it comes to a momentary rest below the horizontal diameter OC. Through O, and then retraces back its path, that is, it oscillates about this A point. इस तरह की मोशन यहाँ ये करेगा, oscillates about A. In case second, velocity v and tension T both vanishes, and so it means height from A for both is same, that is h1 equals to h2. And in this case, using value of h1 from equation 9 and value of h2 from equation 11, from 9 and 11 we get u square upon 2g equals to u square plus ag upon 3g, or which gives u equals to under root of 2ag. So using this, cos theta 1 equals to cos theta 2, and which will be 0, or in this case theta 1 equals to theta 2 equals to pi by 2. So if the particle is projected with the horizontal velocity under root of 2gh, then it rises up to the level of the horizontal diameter through O and oscillates about A in the semicircular arc C semicircular arc, this one, like that. And finally, in case third, the tension T vanishes before the velocity v, so h1 greater than h2, and in this case we get u is greater than under root of 2ag, and in this case if u is greater than 2ag, then from equation 10 cos of theta 2 is negative, as u square greater than 2ag, so cos theta 2 is negative from 10, where t equals to 0, then theta 2 as cos of theta 2 is negative, so theta 2 is an obtuse angle, um, which is that is greater than 90 degree. So now at the point where the tension T vanishes, see in this figure at theta 2 equals to, which is more than pi by 2, P पॉइंट पर टेंशन हम देख रहे हैं कि P पॉइंट पर टेंशन जीरो है, बट ड्यू टू वेलोसिटी पार्टिकल विल मूव फ्रीली आफ्टर पॉइंट P up to Q, where this motion is projectile motion. So now at the point where the tension T vanishes, the string becomes slack, and since the velocity v is not zero, the particle leaves the circular path and then describes a parabolic path freely under the gravity. Hence, if the particle is projected with the horizontal velocity more than under root of 2 ag and less than under root of 5 ag, because up to under root of 5 ag or more than under root of 5 ag, we already discussed that it will describe circular path. But if velocity u lies between under root of 2 ag and under root of 5 ag, at obtuse angle, this circular path will become in the form of projectile. Then it rises above the level of the horizontal diameter through O and leaves the circular path at a point somewhere between horizontal through O and highest point, and describes a parabolic path. So this is the motion we have discussed inside the circle. That particle projected from lowest point A with velocity u